Hello everyone, I'm Barani Mohan. I'm product manager for MapleMBSE. So in today's webinar, what we will see is we'll see an overview of what MapleMBSE is, what, what is the use case that we are trying to achieve with MapleMBSE, and then we'll get into the safety analysis. I'm not going to explain to you a whole uh, list of different functionalities or different tools that you are going to be using to perform the safety analysis. I'm just going to give you a very quick brief in order for me to set the scope and for me to set what we are going to see in today's demo using MapleMBSE and how we are going to perform parts of safety analysis. So I'm not going to show you the demo for doing a complete safety analysis, but we are going to show you some essentials for using MapleMBSE in a very simple way. And this is being focused on users who are not familiar with the MBSE process or the modeling language and the modeling tool. So now, in your organization, if you have been using MBSE or if you are looking into adopting to MBSE, one of the main challenges, we have the system engineers who are familiar with the modeling tool. They know the modeling languages, they know the process, they understand how the system model or the system model has to be built in. And this model is being stored in a centralized place. And say the system model, which has all the relevant information that you need as an authoritative source of truth. And from this system model, you can break it down, or you can find the different components of the system, the structural aspect, which is the physical layers of the system. You can find the functional aspect, which is the behavior of the system. What are the requirements the system has to satisfy, and the different constraints, which are the parameters. So all these are being stored in a centralized place. And the system engineers build the system model either based on modeling languages like SysML, you can use Arcadia, or if it's based on UML, etc. One of the main challenges here is how these system engineers can bring in different project stakeholders. So the project stakeholders here are the safety engineers, they could be the program managers, they could be the requirements managing engineer, etc., or the design engineers. How to get information or how to make these stakeholders involved into collaborating and creating a more useful system model. So this has always been a challenge because these stakeholders, not everyone is familiar with the process. They are not familiar with the modeling language. They don't have the idea behind how SysML works, etc. Now, the typical use case to solve this problem has been some information from the system model is given to these project stakeholders. And these stakeholders now, based on the information that is provided to them, they do some reviews, they add their comments, they add certain information that has to go into the model in terms of, say, documents, spreadsheets, or this is being communicated back using emails. So this is where the problem occurs. This is where there's a friction between the stakeholders and SysML and the interaction between these two and how the system engineer is able to manage these two. And this leads to miscommunications because the way the stakeholders meant could be completely different from how the system engineer interpreted those. It's waste of time. You need to do a lot of reviews. There are misinterpretation, etc. And what MapleMBSE offers is a solution for specifically this problem. So instead of detaching the information from the SysML model or the system model and giving it into the hands of stakeholders, provide a means of the stakeholders to directly access the SysML model or the system model. So from this, they could make the design changes, they could contribute the relevant information. And the other important thing is we can create task-specific views. So for example, if it's just an engineer who has to manage the requirements or another engineer, like say a product manager who has to review certain milestones in the model or certain decisions that has to be made by this project manager, he's not concerned with whole lot of information that is available in the model. So there is so many information. There is a lot of irrelevant information in the view of product manager. So for him, give a very task perspective. For a safety engineer, give the view on for which part of the model or for which subsystem of the model he has to perform his safety analysis. And the solution that MapleMBSE offers here is using a very familiar tool to interact with the SysML model or the system model. So that is through Excel. So what MapleMBSE offers is you interact with the SysML model, you interact with the same information the system engineer has access to. You also have always the most recent changes, the latest changes that's available in this system model. And now you can provide the information in more relevant way. So the information that is being saved from the stakeholders is relevant to the system model. It is synchronized with the whole model. You are not exporting a view and then working on it, then importing it. You are provided access to this system model through Excel. So the project stakeholders interact to the system model using tables they see in Excel. So that's what MapleMBSE offers. And to understand better how MapleMBSE works, how it could help with collaboration, please look into our previous webinars to have more detailed information on it. So now what this facilitates is it's easy for doing design reviews now, since all the information is now in a centralized place. In addition to the task-specific views, we can create views for performing FMEA, safety analysis, trade study, etc. And all these information are bidirectional. So any change now the system engineer makes, it's also reflected to the view the stakeholder has. Changes that stakeholder makes, it's again saved to the centralized system model from which the system engineer also has access to. So everyone interacts with the same information, they interact with the most recent information that's available with the system model. Now, what are the advantages of this is it now broadens the engagement with the system engineering process. So in addition to the system engineer working with the system models that's based on SysML, now you can have different departments who also have access to the same information, and they can all collaborate into providing more information, or much relevant information is added to the model now. Now, again, since it's Excel, it's very easy to explain and get the information from the stakeholders. So it does not involve a lot of training. They don't need to understand the complexity of the modeling language. They don't need to understand what SysML is. Everything is provided as a specific task now to these different departments or different stakeholders, and they just interact with the tables. But on the back end, it's MapleMBSE doing all those transformation and transforming their changes as a SysML model. And now, since everyone has access to it, it is easy to reduce the error, reduce the cost of mistakes that happens through transactions that has been detached from the model. So they could be working with the revision that has been older. But now, since everything is centralized, you reduce cost, you reduce the errors that could creep in. And in addition to this, the backend is completely flexible, because it's very hard for us or for anyone to create a tool that will generalize or that will satisfy the needs of different organizations. So that's why the backend is completely customizable, that you can tailor it to different projects within your organization, or it could be tailored to different organization based on the different MBSE process or the way of your modeling with SysML or other modeling language. Now, like I mentioned, for more information for you to understand MapleMBSE, we have a previous webinars. You can get access to it by visiting MapleMBSE.com. So now let's look into the safety engineering part of today's webinar. So to give you just a short brief of what safety engineering is, what are the different tools and the scope of today's webinar. So the main objective of safety engineering is to include safety related requirements into system design. So when you're designing a system, we want to include this extra factor of safety. This could be to reduce the risk, to reduce the cost associated with the risk, to improve the reliability. So for example, if it's on the aviation side, you need to follow this ARP 4761 safety assessment to get certified. So similarly, ISO 26262, this is related to automobiles, specifically for the safety standards for electrical and electronic systems. So similar to this, there could be different standards based on different domains. And I'm today, for today's webinar, I'm going to focus on the ARP 4761 part. So again, for performing your safety analysis or the safety assessment, there are different tools like the functional hazard analysis. You can have the failure mode effect analysis. There are so many different types of tools that you can use to assess safety. And the guidelines like ARP 4761 or the ISO 26262, they provide the guidelines, they provide the methodology to access this or assess the safety part of your system. Now, again, to set a focus on what will be today's scope, I'm going to focus on function hazard analysis. We are going to identify failure, identify the constraints of the failure and how severe it is. And the function hazard analysis, this could be performed on two levels. One is the aircraft level, considering aircraft as a whole system, and then the system levels like different subsystems of the aircraft. The other tool that we are going to see today is failure mode and effect analysis. What I'm going to do today is to take the functions that I've defined for a model in SysML. I'm going to perform the function hazard analysis and also failure mode effect analysis. So when you consider the traditional safety assessment process using a V, so this is what it's going to look like. You'll have the system requirements, perform the aircraft level hazard analysis, then break it down to system level hazard analysis, do a FTA, so that's the fault tree analysis to identify the source of the fault, based on which, or based on the previous three tools like the FHA or FTAs, we determine the safety requirements. Now there are new requirements in order to ensure safety of my system. So the system will be designed to satisfy these new safety requirements. And then towards the top approach of the V, we do the FMEAs on the system level. We do the same kind of top-down approach, but from here, bottom to top, right? And then finally, with the ARP, we'll have the certification based on this process. So we'll do the FHA, that is the functional hazard analysis. We'll do the FMEA, and we'll see how we could add new derived safety requirements back into the SysML model. So in order to do this, using Cameo, what I did is I have created a model of an UAV already, and I have extended the profile of SysML to add new elements that I'm going to capture based on my my functional hazard analysis and my failure mode and effect analysis. So I have different stereotypes that I've defined for the elements that I'm going to create, and based on these stereotypes, I've defined new attribute values like ID, what are the failures, the different terms that I need or that I need to capture from the safety engineer. So so before I could go to the workflow, let me show you the model. So here, I'm going to first start with showing you the model and how it's being defined in SysML. And then I'm going to go back to MapleMBSE, and we are going to see how a safety engineer can access this information and add this input into the model. So this is the model of an UAV, and the mission requirement is to strengthen the firefighting operation and for using an UAV to put down fires of forest fires at remote areas. So I have different requirements or different requirements based on which the complete mission is relied on. And the use case, this is the different use cases of how the UAV will be used by the different departments that's involved. And here we have the list of, or we have the UAV within the operation domain. So where it's being operated, what are the different functions that will be focused, what is the system of interest. So these information are from the operation domain. So this is where our focus is. We are going to identify the failures of the UAV's functions. So as a black box, so these are the parts of my complete UAV system. So one is the ground control system, the other one is the UAV itself. What are the different operations that I'm being, or operations that are expected out of my UAV. So now let me go back to my slides. So here, to define the workflow, I'm going to bring in the UAV system function into MapleMBSE. We are going to identify the failures for it. And based on the failures that we identify, we are going to find what are the effect of the failure, what is the criticality, and we are going to add in some comments like a justification of why we think this, why we have assigned this certain criticality for the failure that we have identified. So this is the workflow for the function hazard analysis, and for the FMEA part, this is the workflow that we are going to follow. I'm going to bring in the same system functions. So we are going to start with the system functions again. What I'm going to do here is identify the failure modes, which is going to be very similar to the previous one. But the difference here is I'm going to create a failure mode effect analysis table here. So I'm going to define what is the severity, define what is the occurrence and detection. So by severity, I'm going to tell how severe it is. And in a scale of 1 to 10, I'm going to, 10 would be the highest. So based on this scale, I'm going to determine a severity number. And occurrence, so this is how frequent I'm expecting this failure to occur. And again, based on scale of 1 to 10, where 10 being the highest, I'm going to provide or define the number for occurrence 2. And D is the detection. How easy it is for me to detect this failure before it occurs, or how easy it is to detect this failure once it occurs. And based on these numbers, so I'm going to calculate the risk priority number. So my risk priority number is the product of my severity, occurrence, and detection. And also I'm going to calculate the criticality, which is going to be the product of the severity and occurrence. And based on these failures that we have captured, we are going to add new requirements into the model in a way of actions that is going to mitigate these failures that we identified. And then the complete workflow would be once this failure is again added back to the system model. Now the system model will be again iterated to satisfy these new safety requirements that has been put in place. And again, will be asking the question to ourselves that do I feel or am I satisfied if my system is safe? If answer is no, we are going to again perform, or we are going to again iterate through the same process until we get the answer as yes for if is my system safe enough, and if it says, we move on to the other way. But for today's workflow, I'm just going to add these requirements into the model, and we are going to see these as how MapleMBSE could transform these as SML elements. So I'm going to launch MapleMBSE now. So I've launched it. It's in my other screen. I'm going to drop it to the screen that I'm sharing. Just a second. So here, once I launch MapleMBSE, this is the login screen for today's uh, demo. What I'm going to do is I'm going to connect with Teamwork Cloud server, and I'm going to access the model information from the server. We are going to see it as tables in MapleMBSE, make changes to it, save it back to the model, and then I'm going to use Cameo Systems Modeler to see the changes that we have made. So that is the same tool that we initially saw when I explained the contents of the model. So here, this is my login screen. Other important things that I wanted to mention here is, so now based on the username and the permissions and the roles assigned by the server administrator, I can restrict the number of projects that is visible to the user who is going to work on the model. And you have the option to select the different branch that you work on. So now when I click on OK, what MapleMBSE will do is it is going to access the server model, and based on the template that I've already defined. So by template, I'm meaning that what the customizable part I mentioned before few slides. That MapleMBSE is completely configurable, and I have made the configuration in a way that it fits the workflow that I just defined. So here in Excel, I brought all the contents of my model. So on the top, you can see that I have accessed the Teamwork Cloud server and accessing the SysML model, and it shows my username, the branch that I have connected to, the revision number that I have connected to. So if I get back to Cameo Systems Modeler, you can see the same model that I've been working with on Cameo. So it's the same SysML model, and I'm connected to trunk on the same revision number, which is 60. So here, these are the list of system functions that is available for my UAV system. For example, like the analyze the feeds, capture continuous feed, etc. Now, there are different tables with information of the model. So you can consider each of these tables as a different view that access the model and it's being displayed to the user. So here, this is the view of the functional hazard analysis. So I have only one system function for which I have identified failure, effect, and criticality. So now I'm going to focus on a different system function, identify the failure for it, and we are going to add the effect and criticality. So here, based on the functions that's already available in the model, so as a system engineer, this scope would have already been defined. So here you can see, initially we saw that the model has a lot of different information like the structure of the model, the different components, we have the requirements that is defined, the interfaces. But for a safety engineer, his focus is more on towards the part of the model using which he has to perform the safety analysis. So here you can see only the system functions. The safety engineer is not provided or given the complete model, or he's not overwhelmed by the information that is available in the model. I'm giving him very simple view of just the list of system functions. So now, based on the system functions we saw on the previous table, like I can select one of the functions for which I want to identify failure. Say, I want to work with analyze feed. So this is the function, or this is the system function for which I'm going to identify the failure. So for analyze feed is based on some components that I add to the UAV, it has to automatically say, capture the feed, analyze the hotspot for where the fire is. So say the flight path could be automatically tracked or added. So that's what the system function analyze feed is for. And the failure would be, I'm just going to say fail to identify the hotspots. So this is my failure, that it's not able to identify the hotspot, maybe because of failure with the heat sensor component or etc. And the effect of this failure is, in the something like I cannot find the hotspot to drop the payload. And again, I've already defined the criticality. So the criticality could be chosen from the list of 4 options. One is no effect, but this failure will not affect my mission in any way. Then the minor is that there is a little effect, but it's not hazardous or catastrophic that it will be a problem for the mission itself. And hazardous is it's problematic, but it's not going to leave, or it's not going to lead to the complete failure of mission. And catastrophic is like there is no recovery from it. The mission or why we started this project itself will fail if this specific function fails. Say for the analyze feed, even if I'm not able to say identify the hotspot or identify exactly where there are fire in the remote places of the forest, it's hazardous that it's still a problem for me, but it's not catastrophic. So a justification or comment why, as a safety engineer, I think that this is hazardous, not catastrophic, or there is no effect. So that's the comment that I'm expecting from the safety engineer here. So say for this, I'm going to tell this failure can be something like overcome. So even if I'm not able to, or if the UAV is not able to automatically analyze the feed, the pilot, he can control remotely the UAV, and he could use the visual from the video to identify those spots. So I'm not saying that this is catastrophic, but just say I'm giving a criticality as hazardous. So let me save just this part of the model, and then we'll get back to the rest of it. So this is the workflow for functional hazard analysis. So similar to this, I can identify failures for all the system function. I can identify multiple failures for one system function too, and I can save it back to the model. So now I've identified one failure. Now I want to save this to my system model or the system model. So I double click on the save button. So I get a commit message. So I'm going to add a commit message as new failure for functional hazard analysis, and I'm going to click OK. And on the top, you could see that we have changed from revision 60 to revision 61. And same way, for me to access the revision here or to view the changes in Cameo, I'm going to update my model. So once I update my model, it's going to access the latest information from Teamwork Cloud, and I'm going to see the changes that I recently added. So the changes were added to the system behavior inside the function hazard package. I'm going to log this. So here, this is the failure that we identified to identify the hotspot, and this was to analyze feed. So here you can see that we created a dependency. So it has a stereotype based on the profile that I initially showed in the slide, that this failed to identify the hotspot as identified FHA for the function analyze feed. And here you can see the comments we added, the criticality and the effect of the failure. So as you can again see, the user or the safety engineer who was working on the Excel part of the safety analysis process, he did not need to understand, or he did not have the restriction in understanding what an activity is, what is a dependency, and what kind of stereotype the dependency should have, and what are the different kind of information, or what an class is, what a stereotype is. how we have to add these information as tags in SysML. So all these that I explained are related to SysML, but for a safety engineer, he is not concerned, or maybe he is not familiar with these information from the SysML. So for him, it's very easy now to interact just with using tables. He added information very simple as a way of how you traditionally use Excel. But these information has been captured as the SysML elements here. And the other thing is in the whole model now, as you can see, that there are so many information that's available in the model, but we have created a task-specific view for performing just the safety analysis. Now, I'm going to go into the second workflow where we are going to identify the failure modes. This is generally done, say, with the components of the UAV, etc. But I'm going to continue with the system function itself. So this is the same list of system functions that you saw in the activities table. So I have the system function and I have the failure modes that are defined here. Say now I want to identify another failure mode for drop payload. So I'm providing a ID for the failure mode. And I'm going to call this as payload. Sure. I have given an ID and the name for the failure mode. Now I want to link it to the failure to drop payload. So what I'm going to do is just I'm adding an X, meaning that I want to create or I want to add a kind of a relationship that this failure mode, FMEA 08, is linked to the drop payload function. Now, in the other table, this is the same information. You can see that FMEA 08 is linked to the drop payload, but this is the table where I'm going to add all those information for the FMEA, like the severity, occurrence, and detection. So here, I'm going to give a description for the failure. So fail to drop payload. So the payload here will be either some agent that is going to extinguish the fire or water. And say I'm saying that a description that the payload cannot be desired location. And the severity is this is quite high because the whole mission is to put out fire, and if I'm not able to drop my payload, in this case, which is either water or the fire extinguishing agent, so that's quite serious. So I'm giving it a very high number of 9, and the cost is say the payload drop, the payload drop lever or the door is jammed. So the reason or the cause of the failure is either some kind of actuator problem or something that happened that it prevents me to drop the payload. And the occurrences, this is not a failure that occurs very frequently because the actuators are more reliable. They have been tested and they have been developed for so long. So occurrence is very, very less. Say I'm going to give a number of 4. So it's on the lower side. And the detection is, so the failure, I'm just going to say that it's hard to detect failure actuator. So since it's hard to detect, I'm going to give it a value of 7. Say this is how hard, on a scale of 1 to 10, 10 is the highest, so I'm on the higher side. So I'm saying that it's quite hard to detect failure if it happens with the actuator. So for criticality, I'm just going to calculate the product of these two. And now since it's Excel, I can use either macros or use Excel formulas to perform these calculations. So it's 36, and then risk priority number is nothing but product of my severity, occurrence, and detection. Again, I'm writing the product of all 3. So this is my risk priority number. For the failure, fail to drop payload, which I have identified for the function drop payload. So now the next view is where I want to add the derived failure mode requirement. So based on the failures that I have identified, I want to add requirements, and also between the failure modes, like here we have the system functions, we have the failures defined here, and then we want to also now add requirements to the model. But we want to make sure that all these information are connected. If they are all represented as an individual component in the model, that there is no link between them, we cannot use the most useful feature of XML or the MBSE is using the traceability to identify the components or what led to the components. So that's why we are kind of creating these links between the system functions, same way for the failure modes. Similarly, for requirements too, I'm going to perform the same thing. I'm going to create a new requirement, but I want to also link it to the failure which led to this new requirement. So I'm going to create a new requirement. So this is the ID with which I want to add the requirement. So this is I'm going to call this requirement as payload drop door requirement. So I have added a new requirement, and now I also want to link this newly created requirement with the failure we identified. So here I'm creating a link. If I go back to the previous table, you can see that I have linked the failure FMEA 08 and FMEA R04. So here again, the user doesn't need to worry about if this link is, say, if it's kind of a dependency, or if what kind of dependency it is, if all this complexity is hidden. So here we have now the requirement being listed. So I have all the 4 requirements or 3 requirements that are already available. So this is my 4th requirement that I have added to the model for payload drop down. And say the specification is something like that should be something like that should be a mechanism to test the control during system startup. So I want to add something like auto maintenance check where every time we start the system. So there. So this is what, or this is the new requirement. But it's not more formal, but just to show you an idea of what could be done. So I have created the requirement, added the specification. Now again, like I mentioned before, I want to save it to the model. So all those changes that I made in the table is now saved to a centralized place. So again, the same process. I'm going to double click on the save button. New failure mode. I'm just adding a message saying I've identified new failure mode for system function. And now I have saved it. And on the top, again, you can see that we were working with revision 61. Now we are at revision 62. If I go back to Cameo, you can still see that we are in 61. With the latest changes, I'm going to update my project. So for this part, all the changes that we added using MapleMBSE will be inside the system behaviors and the FMEA package. We'll go ahead and lock the diagram. So the failure that we added is fail to drop payload. It's the function, and the requirement we added is this. So here you can see that we initially started with the activity. We identify the failure for the activity, like we define the different terms for it, like what is the risk priority number, the severity, occurrence, detection, etc. We identify the cause, how hard it is to detect or how to detect. So these information can go in here. The explanation for the failure, and you can see that we are still maintaining the traceability. This is a different dependency with a, this is a dependency with a different stereotype compared to the derived FMEA. So we have created a requirement, given an ID for it, a text for it. Again, we can still maintain the traceability to check that this requirement has come up because of this failure or fail to drop payload. Similarly, like this is the workflow that could be performed with all these system functions. And now, as a safety engineer, now I don't need to understand the complexity. I don't need to understand what a dependency is, the stereotypes is, what are tag values, how I need to add information into the tag values. So all these informations are shown as relevant table. They are shown with the relevant scope to the workflow of a safety engineer, and he can now easily interact with the system model. So he's not interacting with the detached information from the centralized model. He is working on the information that is most relevant, that's most recent and relevant to his work process. So the other question or another common question that comes up is how this could be collaborated between engineers. So similar to how Cameo or interacts with the teamwork load model, when a user starts editing an example, when I started editing this table here, where I have the system functions or FMEA, I would automatically obtain logs for this element in my model. Say, for example, I'm adding a new failure mode. Call this test failure. Share. And if I go back to Cameo, and if I update my model, you can see that I have obtained logs for this. So here you can see that I have obtained logs to the FMEA package. So this is the username with which I have logged in MapleMBSE, and based on by this, I'll be able to avoid the conflict of different users working on the same part of the model. So if there is a different user, he has logged in either using Cameo or Magic Draw or using MapleMBSE, and when he tries to add something here, we will be able to see that information that is being displayed in MapleMBSE or in Cameo, you will see it like this. In MapleMBSE, the information that you will see is the element cannot be logged because it's being logged by a different user. So this way, we can bring in different users collaborating at the same time and working on the different parts of the model. And since, or as you can see that I have obtained log only for this package, so that there could be different users who have logged in using the other tools and work on the different part of the model. So we have specifically working, or we have obtained log for this. And if I close MapleMBSE now, so say I've added my changes, I want to close MapleMBSE. So now when I close MapleMBSE and my logs will be automatically released here. You can see that I'll automatically lose logs for the FMEA package. So the user again doesn't need to worry about the part of the model he's working with. If no one is working with, he'll acquire logs automatically and add his information there. And if he saves and closes it, MapleMBSE will automatically release all the logs. This is very useful when working together as a collaborative way in the project.